I'd like to thank the organizers for providing me these opportunities to present the recent heavy flavor measurement with the Atlas detector here. So I guess people here in this workshop really likes heavy flavors, so I don't need to motivate that because they are produced early in the conditions and that experience the entire evolution of the QGP, and its productions in vacuum could be calculated perturbatively. But still, the heavy flavor production in Taiwan conditions is a complicated business because we have to deal with the medium transport properties and energy loss and also the hadronizations. So personally, I do think that there's a value to provide more detailed differential measurement of simple observables like RA and Vn of heavy flavors in order to help to constrain the modelings of each part. So in Atlas, we are now focusing on using the semi-electronic decay muons to probe the heavy flavor productions. So there are a few advantages of using muons because first, it's very clean, especially in the central conditions, because the background is more suppressed than the signals. And from experimental point of view, the muons are very easy to collect because we can use muon triggers. And then we can also extract the charm and the bottom contributions at the same time. But unfortunately, in a correlated way, I'll talk a little bit about that later. So in the plot showing on the left, that's the how we use the momentum measurement in different part of the detector to remove the background contributions in the selected muon samples. And the plot on the right shows you the fading procedures that we use to separate the charm and the bottom contributions based on their the muon displacement from the interaction point due to the fact that most of the charm hadrons has significantly shorter lifetime than the bottom hadrons. But we have to keep in mind that when we compare the muon results with the hadron results, there is this kinematic decay difference, the kinematic difference caused by the hadron to muon decays. Okay, so the Atlas has performed several measurements for the muons. So the first two are the Vn and RA had 2.760 TeV net conditions and V2 in P-light conditions for inclusive heavy flavor muons. But recently, since we implemented these techniques to separate charm and bottom contributions, so we have measured V2 for charm and bottom muon separately in PP conditions and V and RA in the net conditions. So here you can find the links to the publications and also the links to the Atlas publication website, where you can find a lot of useful auxiliary materials which are not included as part of the journal publication. So in my talk, I will just focusing on the recent measurements with the charm and bottom contribution separated. Okay, so first let's look at the heavy flavor production in the PP conditions at 5 TeV. So what's showing here is the measured charm muon cross-section, differential cross-section as function of PT on the left, and the bottom muon cross-section on the right. They are both compared to the follow calculations, and in the lower panel, you can see the data to follow ratio. So in the charm part, so the data ratio lies at the upper boundaries of the follow calculation uncertainties. So the uncertainties include all the uncertainties of renormalization scales and factorization scales, and also the mass dependence and PDF dependence. And on the right, when you look at the bottom, so it looks very similar as the charm at low PT, but if you move to higher PT, the data updates with the follow central values very well. And so the observed data follow difference actually looks quite consistent with other heavy flavor measurement. For example, this measurement from Alice for various of dimensions. So that means this indicates that even though we have so the PQCD calculations of heavy flavor production in PP are doing a very good job. So they are not very different from the measured results, but they are not perfect. So we need to keep that in mind. And then move on to the net conditions. So we measured both the RA and Vn as function of PT and the centrality. So what I'm showing here are the measured RA on the top row and the measured V2 in the bottom row as a function of PT. So the left column is for 0 to 10% centrality, and the right column is for 40 to 60, which is the most peripheral beam that had been measured. scatters. So in each plot, the blue points are the charm muon results, and the red open circles are the bottom muon results. So if you look at RA results, so at low PT, clearly the charm muon RA is lower than the bottom muon RA, and the difference becomes smaller and insignificant as we move to higher PT above, basically above 10 GeV. We cannot conclude any difference from the data points. And then for the wave 2 results measured with event time method, so you can see that both the charm and the bottom are significantly non-zero, and the charm muon wave 2 is significantly larger than the bottom muon wave 2. And in peripheral conditions at higher PD, so the difference becomes insignificant within the larger uncertainties. And both the RA and wave 2 measurements show some relatively strong centrality dependence. So yeah, as we expected, we observed the difference in the charm and the bottom productions in the heavy ion conditions, and the charm is is impacted strongly with the interaction with the medium. So let's move on to some model comparisons. First, I pick up a transport model and an energy loss model. So the transport model, that mode, which is a pure Langevin framework inside a 2+1D medium, showing as the solid color lines in each plot. And the energy loss model is the dynamic, radiative, and collisional energy loss within a 1+1D ideal Biot medium called DNAB, showing as the color band. So you can see for the RA results, so both models basically reasonably describe the measured RA results, especially at higher PT. But if you focus on the V2 results, so the calculations from DNAB, which is the energy loss model, captures both the PT dependence, the centrality dependence, and also the mass orderings of the measured charm and bottom muon V2. While the pure Langevin calculations from that mode fail to describe the V2 measuring in data, and some PT ranges, so it predicts incorrect mass orderings. But a good thing about the DAP mode is that it's a modular framework, so one can easily replace the Langevin framework with some energy loss along a straight line of the evolutions. So here I'm adding the comparisons of the DAP mode with pure Langevin with the DAP mode plus constant energy loss. So the energy loss points are showing as the dashed lines in the plot. If you look at the wave 2 results, so definitely adding the energy loss leads to a better description of the data of wave 2 for both the charm and the bottom, and it has the red magnitude and the red mass orderings. But at the same time, switching to the pure energy, the pure constant energy loss model, it leads to a larger discrepancy between the calculations and the measured data results. So currently within the DAP mode approach, there's no consistent description of both RA and wave 2 for both charm and bottom. So another model we have picked up here is this I call it CCNU model, lead by groups at CCNU. So it has a quite similar setup as the DAP mode. It has a Langevin hydrodynamic framework with hybrid hydrolyzation model. So the difference is that in this Langevin implementations, you use a modified form with additional radiative energy loss contributions compared to the DAP mode. So with this setup, you can see that at peripheral conditions, it predicts, so the calculations roughly describes the measured RAA for charm and bottom and V2 for charm and bottom. But the problem is if we move to more central conditions, you see that the predicted bottom muon RAA and V2 are significantly larger than what have been measured in data, which is quite surprising because a larger RAA and larger V2 means different magnitude of the interaction. So I guess with all these comparisons, so the one thing I need to point out that in the measured PT range from 4 to 20 GeV or 30 GeV, it seems that it's dominated by the effect of the passiveness or the differential energy loss of the heavy flavors. So unfortunately, we don't have easy access to the lower PT, so our results are not very sensitive to the transport property of the medium. So another way to look at our data is to make scatter plot. So for plots showing on this slide, so the x-axis is the measured V2 values, and the RAA, the y-axis is the measured RAA values. And each point is a different centrality bins, and from the left to right, we are moving from a low PT to high PT. And again, the blue points on top are for the charm muons, and the red points in the bottom are for the bottom muons. So here you can clearly see how the correlation between V2 and RA changes with centrality and PT for both charm and bottoms. And what also showing on the plot are the calculations from Drenaby and DAP mode with pure Langevin implementation. Yeah, and now you can clearly see how how the model predicts the correlations and how does that compare with the data. So hopefully we hope that it could be this type of plot could be also useful for the theory community. So ATAS has also measured the V3 of charm and bottom muons. So the measured results as function PT are showing here. So the upper figure is for central conditions and the lower figure is for peripheral conditions. So similar to previous plot, the blue points are for the charm muon and the red points are for the bottom muons. So basically the charm muon V3 is significantly non-zero, while the bottom muon V3 is just consistent with zero within the uncertainties. And they don't seem to have a strong dependence on centrality. And in the DAP mode, Langevin setup, because it used the 2+1D hydro with event by event fluctuation, so it predicts the charm and bottom muon V3 as well. So you can see the predicted value showing as the solid color lines. So it predicts a larger V3 for the charm muon at the low PT, but as it moves to higher PT, so the difference between charm and bottom becomes insignificant and both goes to zero, which looks different from what has been measured in data. Okay, since we extract the charm and bottom contributions at the same time, so we could quantify the relative difference between charm and bottom using for the RA using the double ratio. So basically, it's the ratio of the charm muons over the RA of the charm muons over the RA of the bottom muons. So showing here are the double ratio of functional PT for central conditions on top and the peripheral conditions in the bottom. So unfortunately, because they are extracted in a correlated way, so there are larger uncertainties due to the strong anti-correlations between the charm and the bottom yields. But even with the larger uncertainties, we can confidently conclude that the charm is more suppressed than the bottom at low PT. And this double ratio doesn't really have a strong dependence on centralities. So which may indicate that the difference between charm and bottom suppression is driven by their difference in mass, and it's not quite sensitive to the temperature of the medium. And what also showing on the figures are the calculations from DAP mode and the Drenaby. So they both predict a very similar charm and bottom difference. So you can see at central conditions at low PT, there's a quite large discrepancies between the data and the model predictions. Okay, so with the same idea to quantify the relative difference between charm and the bottoms, we can also do that for the VN measurement as well. So what's shown here on the left is the measured from top panel to the lower panel is the measured RAA, V2 and V3 for charm and bottom muons. And on the right plot shows the relative difference. So for the RAA, we take the double ratios, and for the VN measurement, we take the absolute difference. So the uncertainties has already taken into account the anti-correlations between the extracted charm and the bottom yields. So hopefully this could be useful for the communities as well in order to better quantify the driving factors of the charm bottom difference. So how does our results compare to other experiments? So first we compare the charm muons results with prompt D0 measurement from CMS and ANIS. So the upper figure is the measured RA in 0 to 10% as function PT. So the black points are the ATAS measurement in comparison to the color points of prompt D0 methods from ANIS and CMS. Because as I mentioned earlier, we need to take into account the difference between hadrons and muons due to the decay. So we also add the GNAB calculations for both the hadrons and the muons from the D0 hadron decays. So you can see that in 0 to 10% centralities, the difference we see in the data between muon and hadrons is larger than what the model predicts. But I'd like to point out that so to do the hadron to muon decays, we need to use the spectra instead of RA alone. So even if the RA is well described by the model, doesn't mean that the spectra is well described by the model, because as I showed earlier, the spectra in PP may not be not be as perfect as we would like. And for the way to measurement, you can see that the models predicts a very small difference, and which is consistent with what we see in the data. So the muon way2 is just consistent with the dihadron way2. And for the bottom part, we compare the muon results with other BDK products of D0 mesons and GSIs. I think Yanjie has already showed this plot in his slides. We also add the GW predictions for the hadrons and the muons here as well. So you can see that all the BDK products shows a very similar results, and the measured results are significantly smaller than what GNAB predicts. Okay, so we use very similar techniques to separate charm and bottom muon contribution in PP conditions, and measured the charm bottom muon way2 using muon hadron two particle correlations in the 13 TeV PP conditions, and with a template-based non-flow subtraction. So the measured results of the charm muon way2 are shown here as the blue points, and the bottom muon way2 are shown here as the red points of function PT. They are compared to the way2 of the inclusive light hadrons, showing as the green points. So you can see that the charm muon way2 are quite similar to the inclusive hadron way2, where the bottom muon way2 is just consistent with 0 within the uncertainties. So one thing I would like to point out that if you compare the way2 results in high multiplicity PP, it looks quite similar as the way3 results in Lennard conditions, where the charm results are significantly non-zero with a very similar PT dependence in the two measurement, and the bottom results are basically consistent with 0. But I don't really know the connections between, or if there are any connections between these two measurements. So to understand the results we observed in the PP conditions, so there could be different interpretations. First, maybe there might be small droplet of the Quark-Gluon plasma in high multiplicity PP conditions. So there's also differential interactions that changes the angular distributions of the heavy flavor hadrons of heavy wave quarks. Or there could be different interpretations for the origin of way2 in PP and Lennard conditions. But the follow-up question is really, no matter what interpretation you'd like to propose, you need to understand, you address the difference between the charm and the bottom. So their mass is not so different, but the resulting way2 or even the way3 in the Lennard conditions are so quite different for the charm and the bottom. So so far, I guess this is still an open question to the community, and we are looking forward to any interpretations or calculations, or even like guidance from the theory communities about what we should be looking at in the future in order to help to address this question for non-zero charm muon weight 2 and zero Polymer muon weight 2 in high multiplicity PP conditions. Okay, so that brings me to my short summaries. So I guess I hope I have convinced you that the decay, subelectronic decay muons serves as very powerful heavy flavor probes in the high beyond conditions, especially for the bottom muons because of its not relatively large statistics and small background contaminations. So there are detailed differential measurements from ATAS available. So don't hesitate to send us your calculations. We can also do the hadron muon decay for you and make figures to show in conferences. So just a small comment about what we should do next in ATAS. So I guess we are confident about our muon extractation techniques. So we are now using it as a tools to study other heavy flavor objects like the jets, or to calibrate other heavy flavor jet tagger. And personally, I also think it worth to revisit the p-data collections with this charm bond suppression techniques before we collect new data. But you know, the ATAS heaven group is small and it's getting smaller. So yeah, to be honest, it's a little bit hard to predict when that measurement will become available. Okay, thanks very much for your attention.
Thanks a lot for this very nice talk, for the proposal for sending you calculations. Are there any calculation foreseen? No, okay, but let's see if there are comments or questions from the audience. Giuseppe.
Well, you mentioned something in this summary. I wonder whether you have planned measurement of angular correlation of heavy flavor. I don't know, even heavy flavor muons with heavy flavor muons or something, target photon with heavy flavor. Given the very spectacular things that the detector could do in this sector.
Yeah, we always have that plan. I need to say, but yeah, we are. Yeah, we don't have enough manpower to do that in a short time. So yeah, there are like internal studies that I can see for like dimuon correlations or muon photon correlations. But we are also waiting for more data in order to have a significant, like a better significance. So hopefully that'll be available after the RHC 1.3.
Thanks. Other questions? Okay, Paul Bernard.
Yeah, somehow a very direct question, because sending predictions and calculation to experimental collaborations, we did this a lot in the past, and of course we have very limited power. Then it costs more time. We get elder. It's a bit more difficult. So what specific, basically, signal or what specific measure do you have as compared to CMS or ALICE?
Yeah. So for example, we have the quantified relative difference between charm and bottom. Maybe this slide is better. So if you could provide us the charm and bottom predictions for both wave 2 and wave 3, as well as their correlations, yeah, we can definitely add them to our future conference talks. As this is a unique feature of this measurement. And we also would like both the hadron and muon results, so that help us to make this kind of comparisons.